Can you guys hear me?
Larissa, where did we put the Zoom link in the Gava town now?
Yes, I shared it. So we're currently live on YouTube, and I'm writing in the chat.
Well, good morning all. It's already 10 o'clock according to my time, but the countdown is still running.
Let's give 30 more seconds.
Right.
Late joinees.
Maybe that countdown page isn't all that precise either.
No, I've set it to 10:01 just in case.
Oh, I see.
Yeah.
I was worried there's something wrong with the clock.
All right. Let's get it started.
Sure, here we go. Yeah, welcome all to this City.AI Nairobi event. Oh, I see I have my Uto background. Yeah, well. So I'm Bastian, part of the ambassador team of City.AI in Nairobi. City.AI is a worldwide network of cities and their AI communities, and particularly applying AI communities. So it's not so much about doing basic AI research and inventing new methods, but it's how companies and other organizations are applying AI for their work and what they do. And this has been running for a couple of years now, with different events happening in different cities around the world. We had our initial event in Nairobi, still at Utu House, back 2 years ago. And during COVID, there was a sort of hiatus of the community. Hello. Welcome. Yes, please mute yourself, so I will mute you. So the COVID has basically put a pause to a lot of activities. And now City.AI is coming back with this AI festival with different cities around the world, having 1 to 3 days of conference days. Today's Nairobi's turn, and we are happy to welcome you all here. I think we have an awesome program of talks today, starting with Laila in a few. But before that, I would also like to introduce the City.AI ambassador team. So of the team, we have Rahul here, and Leah and Shiku. Then there's also Zakia, who hopefully joins us later. So yeah, we are now the new City.AI ambassador team for Nairobi. And we just happen to be all at the same company, Utu. Yeah, Leah, Shiko, if you also can turn on the cameras, please. Just so you have seen us all, at least quickly. Yeah, as I mentioned, there's also Zakia. You can watch her video, which is on the Discord, and yeah, some other channels where Zakia welcomes everybody to this festival. We also call for more participation in the ambassador team from interested people. So yeah, maybe have a look at the City.AI website, and if you like this festival, then maybe this is something you would like to do, then please reach out to us. And we'll be very happy to welcome some more people, and particularly outside of Utu, because yeah, the whole thing is a bit Utu heavy right now. Yeah, that is basically almost all I have to say. Maybe the other ambassadors and I can quickly introduce us personally. So I'm Bastian Blankenburg, CTO at Utu and City.AI Nairobi ambassador. got a background in computer science with a PhD in distributed AI, like game theoretic negotiation algorithms for autonomous agents. That's been a while ago that I worked on that. Since then, I've been working in industry in Berlin for a company building planning software for public transport before joining first Maramoja in Nairobi and then Utu. Maramoja is a taxi app which tries to get people trusted drivers by the idea that there's a lot of mistrust going on generally in Nairobi between drivers and clients. So the idea is to, find somebody who's known by yourself or your friends. And this same mechanism is now also sold by Utu as a SaaS, software as a service, for third-party platforms and shops of all kinds, I mean, web shops. So yeah, we are building this trusted recommendation mechanism there, as we call it, which has some similarities to classical recommender systems, but is very much focused on social connections and also has this personalized idea of trust and applying AI to find out basically who trusts whom. So that's about me. We'll pass it on. Leah, want to introduce yourself?
Morning, everyone. My name is Leah Njuguna. I'm a statistician by training, but a ML engineer by profession. And I'm at Utu, and I run the recommendation system project, whereby we are trying to incorporate social relationships to improve the accuracy of the recommendation system. Thank you.
Thanks. Rahul, want to go next?
Yeah, I'll go next. Good morning, everyone. Glad to have you all here. So my name is Rahul Srivatsa, and I am an economist by training. So I have a master's in economic policy, but post my master's, I've delved into the world of data science myself. So I work with Leah and Bashan quite often, and we are part of the data science team at Utu. I also work as a data scientist for another company called QuickBasket. Over to you, Shiku.
Yeah.
Cool. Good morning, everyone. Welcome all. My name is Shiku Njabi. I'm head of marketing at Utu, and I'm just here to see that everything is running okay. So you'll probably not see me again, but have fun and welcome once again.
Great, thank you, Shiku. Yes, so we are looking at a couple of interesting talks. Are you still, maybe you can share your screen, Rahul, and show the agenda for today? So if you have not had a chance yet, I will just post the link to the boarding kit slides. Oh, sorry, I was talking privately there. So basically, the boarding kit has all the interesting information for today, including this agenda. The first talk's about to start in 5 minutes. All these talks are around applications of AI by local companies or companies having some local context here in their work. There's also a panel about the skill requirements for AI workers. This is centering on the debate how much background in math, statistics, computer science, etc., is needed or not to be a successful AI worker in various roles. There are more slides in the boarding kit which show you the. Are you still sharing, Rahul?
Yeah, can you see my screen?
I can't see it.
Yes, I can see it.
You cannot see it. Okay, great. Yes, there are also the short bios of all the speakers and also the technical information of how to join the various places. So you have found the Zoom link, which was also on the Eventbrite, but then this event is also on GatherTown, which is sort of a virtual conference space where you can walk around with a little avatar and talk to people that you are close to. There's also, at the end of the day, the talent show where some people are presenting their own AI projects or research in some sort of booths that are like little rooms on the map. So I encourage you to try that out. The GatherTown, talk to people there, interact with the talent show presenters there. And if you have any questions, we will also make sure that there's always people of the team somewhere around. So if you're lost, then maybe just walk around until you see somebody from this team that just introduced themselves and just ask them. So how many people here have already looked into GatherTown? Can you raise your hands? Okay, I see
Just
only
two.
one. Well, Rahul, I know you have been there. Leah has also been there, but okay, that's the team, of course. Yeah, okay, so I can only encourage you to try it out because it is quite fun. If you're not so much into fun and you just want to talk to people, then you can also join the Discord. Yeah, all these links are in the boarding kit. The Discord has channels not only for the Nairobi AI event, but also for the other festival events. And yeah, maybe you can even find people around the world to speak to about your interested topics. All right. Anyone, anything to add, comment, questions?
As Bastian mentioned, please reach out if you have any questions on DM or on Discord. I'll be happy to help.
All right. Then we just have about 1 minute to go. And I will just leave it there. Welcome all the people joining.
Hi guys, should I just go?
Yeah, I think that's fine.
Let's wait for the actual start time. Just if we have some very much on time joiners, and then I will introduce Leila quickly, and then she can go. Maybe, yeah, Rahul, unshare your video. I will also unshare my video in a moment.
Yeah, I've stopped sharing.
And your screen, yeah. All right, 10:15. So yes, welcome everybody. For the people who just joined us, we are about to start our first talk by Ms. Laila Lee, who is CEO of Quota AI and a co-founder there, a software company that builds solutions to detect and mitigate AI bias and risks. Laila has quite an impressive background. She's been living on 4 continents in China, the US, Japan, the UK, Netherlands, Kenya, and managed to scale data solutions and tech teams at Philips, Vodafone, and Tesla. Even. She holds 2 bachelor degrees from Boston University and a master's in computer science from Harvard University. And yeah, Leila, I think it's great that we have you here, and I'm very interested in this topic, and yeah, very looking forward to your talk. Please go.
Thank you. Let me know if you guys can see my screen.
Yes.
Great, awesome. So thanks, Bastian, for the introduction. So yeah, this is essentially me. We are here to talk about responsible AI in practice, which is what our company City.AI does. We're building automated responsible AI softwares to try and make technologies more inclusive. So, I probably don't need to tell you guys that algorithms are in every stage of your life right now, from the dating apps that you use to the music, video streaming services you use, and then when you apply for loans, and, even when you apply for jobs, and then when you die, there's technologies and AI tech especially involved. But there are actually quite some risks involved in this as well. So in just under 10 years, AI is going to deliver over $13 trillion of economic activities, but it's estimated that 85% would generate some false results because of bias in data and algorithm. So what exactly is algorithmic bias when we talk about this? A couple of examples is a couple of years ago, Apple Card, their algorithm was found to give men 20 times more credits than women, given the same criteria. And even when the women have, making more money, the algorithm still prefers to give men more credits. And we know there's studies on various facial recognition softwares, and their algorithm have an accuracy of almost 99% in detecting male faces when compared to only 65% accuracy in Black women's faces. And in the US, there's a huge company called United Health. Their Optum algorithm, which is serving over 200 million people, actually showed very drastic racial bias, denying care to 50% qualifying Black patients. And these type of examples are quickly catching up. There's increased media attention to the topic in the past couple of years. You can see, features on New York Times, on Forbes, and I know this year alone, there is a documentary on Netflix called Code Bias. If you guys haven't seen it, you should. And there's huge news about Google, Amazon, and their practices in establishing responsible AI. And not just like in the media, but also when it comes to regulations, there's a lot of regulations coming, changing in the regulatory landscape in Europe and in the US. I think earlier this year in April, there is a new proposed EU AI regulations that will fine company up to 20 million euros or 4% of their global turnovers for AI misuses. And there's already GDPRs and Digital Service Act in Europe that's reinforcing, data privacies and some sort of safeguard when it comes to AI technologies. And in the US, there are laws already made, especially for financial services, when it comes to model development, implementations, and validation guidelines. And there's currently a Algorithmic Accountability Act in the Senate. And I think the government earlier in this month, they actually released a AI auditing framework for all the federal agencies to follow as well. And when it comes to Africa, we can see in Kenya, in Uganda, and in Ethiopia, there are some government bodies looking to establish kind of AI councils or think tank, but the regulations when it comes to responsible adoptions of AI is still lacking. And I think that will quickly catch up because when we observe the technologies that's being implemented on the African continent, most of them are being developed somewhere else, right? Like say a big tech company, they can develop some skin cancer diagnostic tools, and that's being also used in East Africa. But because of the bias samples, it probably doesn't really work on the continent, and there's a lot of adjustments that's needed. So I think regulations on the continent is probably more imminent than before. So where do bias actually come from? So the causes of bias can come from multiple sources. One is that it might be an imbalanced training data set. Like say, we're talking about skin cancer diagnostics, and you might use a lot of different images to train your algorithm. But if the data set is largely of Caucasian skins, then it wouldn't work here. And there's a lot of human bias reflected in the process. So one case in point is Twitter actually taught Microsoft AI chatbot to be very racist in less than a day. So in the beginning of the day, the chatbot is called Tay. So Tay went on Twitter and is learning from everyone that's tweeting at them. So in the beginning of the day, it's saying stuff like, can I just say right now, I'm so stoked to meet you. Humans are super cool. And then by the end of the day, because he has been interacting with all the people from Twitter, it's saying Hitler was right. I hate Jews. So that is from the imbalanced training data set and human bias reflected very much in the training of this chatbot. And another cause of bias might just be model bias. So the example that we talked about before with United Health Optum, so millions of Black patients were affected by the racial bias in their healthcare algorithm because of the model parameter that was set. So the model was set to look for high medical expenditures instead of prioritize needs for care. So what this algorithm does is when there's a pool of patients and there's only limited medical resources, the algorithm is trying to decide who needs the care the most so they can prioritize resources for particular patients. But because it's set to look for high medical expenditures, that just presumes if you need more care, you're going to spend more money, but people don't have money. So it's essentially punishing, poor people, then that's really bad. So we need to examine how we're setting up these models and the parameters in which we're looking for what we're going to actually predict. So the last cause of bias that we can look at is actually concept drift and model drift. What we mean by that is a couple of examples. So if you think about COVID, that actually changed a lot of things of how we shop and how we interact with each other. So if you have an algorithm that's predicting behaviors of people, COVID changed all of that. So your algorithm probably is not as good as predicting the same set of behaviors people might have had pre-COVID versus now. So one example is a clothing retailer, so Stitch Fix. They have a recommendation engine that's predicting people, recommending people, oh, you should buy this, you should buy that. You probably have all seen it, on Jumia, on Amazon, all of these different places that once you buy something, it will tell you people who have bought this also bought other stuff, or you might be interested in XYZ items. So the recommendation engine is probably recommending people like, oh yeah, the holiday seasons are coming up, you should buy this cocktail dress for this party. But because of COVID, all the parties are canceled and no one is doing that anymore. So you can see the sales of athleisure clothes like yoga pants, ties, and leggings actually was surging. So the recommendation engine was out of loop. And that's one form of how the model might drift, because the training data that you train your model on versus the data that the model actually observe in the real world is completely different. So I'm going to pause here for a bit. Anybody has any questions? Immediate questions right now that I can answer? No? Okay, good. Yeah, someone said data changes. Yes, that's very much on point. So when it comes to solving this particular problems, our philosophy is that we need to go beyond the algorithms. If you look at a traditional AI development pipeline, you prep the data and then you build the model, then you start training the model, you evaluate how your model are performing, and then you deploy them, and then you get some sort of feedback after it's implemented. So we shouldn't just look at the data or just looking at the model in itself and audit it and then look for potential bias. We need to look at the whole value chain of this AI development. So what we do is that first step, we need to look at the data, evaluate and mitigate the data bias that might be present in your data set before we even move beyond to the later stage of model. And once you train the model, we need to audit the model for potential bias and how that impacts performance. Because as we know, actually when when fairness improves in a model, the performance sometimes drops, and that has high correlations with the data that's being used. So once we pass that stage of auditing your model, try to correct a bias that might be there because of the data that you use or because of the parameters that you've set, we need to evaluate the model. And there's two parts. One is that we need to look at compliance when it comes to different regulatory requirements in different markets that you're in, and that's the bare minimum that you need to do, right? And then you look at the kind of organizational principles and values that you're trying to address, and say, oh, we're trying, like, one of the core values for an organization is transparency. Like, what does that mean? How do we operationalize that? How do we document all of the data and the models that we have used, and making sure that's proper and right? And the next step is, we all know AI is a black box, and for a lot of non-technical stakeholders that's involved, it's very hard to explain why the model is making certain decisions the way it is. Like, say the example that we use for the healthcare algorithm, people might ask, why am I getting this decision? Like, why is someone else being prioritized over me? And without a proper explainability tool, it's very hard to explain why your models are making these decisions, whether that's biased or not. And then the last part, as we see in a Stitch Fix example, you need to monitor your model behavior and then know when your model needs to be refitted and when that's becoming obsolete. So that's sort of our philosophy, and a couple of things, best practices that we recommend to everyone. Like, in the first step, when it's about uncovering bias in data, so we can use traditional statistics to measure bias and correlations. And the second is that we can evaluate how the data are collected and sourced. So where the data are coming from are super important. And we can ask domain experts to interrogate the high-risk data that's involved. Like, say you're training a healthcare algorithm that's literally going to decide life or death in people, you probably want to ask a couple of domain experts, doctors in the field, whether the data that's used in training is actually appropriate. So that's when it comes to data. And then when we're talking about model and auditing the model, there's a couple of things we can look for when it comes to model fairness, and then the fairness definitions here can vary, depends on what type of applications that you're building. So we can say, the one type of fairness when it comes to model auditing is group fairness. So the model performs equally on key metrics across groups. So in the healthcare example, we can say, the admission rates across all racial groups should be the same, roughly the same, and that's achieving group fairness. Or you can say, we're looking at individual fairness, like similar individuals have equal treatment probabilities. If you think maybe college admission, when it comes to college admission, similar individuals, regardless of their gender, their race, their other backgrounds, if they have similar grades, if they have others, similar achievements, they should have equal treatments of getting admitted to college, right? So this is about individual fairness. Or you can look at altering the sensitive attributes that does not change the prediction. So that's counterfactual fairness. So what does this mean is, if you still take the college application algorithm example, if there's two individuals and they're very similar, and if you change their race, it doesn't really change the outcome. So it doesn't really matter whether they're, Asian or white, they have the similar chance of getting into the same school. So there's a couple of things that we can interrogate the model when we're looking at a already built algorithm. And then the third step is coming to kind of organizational transparency, is we need reporting, because we need to provide context and individual explanations for a given prediction. And that's just your responsibility in building trust with the customers. I think you guys have probably all seen this. Sometimes when you see these ads that Google is pushing you, there is this little question mark that you can click on it, and it says, why am I seeing this? And I think that's one type of transparent reporting that the customer will gradually build trust with, and not just to customers, but internal stakeholders as well. And also we need to give end users the opportunity to explore different model outcomes and find actionable resources. Like say, if you're a bank and then you're using algorithms to decide who to give a loan to and who's not, and your user is getting that decision, but they have no way to appeal this decision, then it's very bad. Like there is a case of Uber in the UK. They were sued by a group of drivers because they use robo-firing algorithms to offboard drivers when the algorithm decides that there are suspicious activities. But the drivers have no way to appeal these decisions, and they were sued, and the drivers actually won the case in the UK, so they have to pay a fine. So in this case, this type of transparent reporting actually will save company a lot of money. And the third stage is we need to document all the data and the model and the building pipelines, so we know where everything came from instead of just a big black box. So we can look at a particular case study. Let me stop here for 1 second and read some of these chats.
Leila, we can have 15 minutes for questions at the end.
Okay. Oh yeah. Okay, then we'll do that at the end. So let's talk about a particular case study. Like if you look at this person in hiring bias, so we all know like in a lot of big companies, they use resume scanners. Amazon built one, and that was discovered to be very racist and very sexist in particular. So when your resume is passing through a resume scanner, what are they actually looking for? So if you look at the case of this one person, went to a good school and has relevant experiences applying for an entry-level engineering job. And another person, very similar background, went to a good school, have relevant experience and applying for the same job. But when the resume are going through the resume scanner, Laura here is automatically rejected. So why is that? So when we look at the Amazon example, like they actually scraped this AI resume scanner, what we found is there's a lot of historic patterns and the model bias that's built into the scanner. So the historic pattern is that if you look at the well of data that they have, people that they have been hiring historically for entry-level engineering jobs are all men. So the algorithm automatically placed more emphasis of looking for men for this particular job. And actually what they found is if in your resume, they actually devalues a woman's female-only colleges, and then in there, if in your hobbies or achievements, you mentioned you're in a women's volleyball team or you're in some sort of women's swimming team, that automatically places you on a lower rank than everybody else. So how we can change that? First of all, we have to start from the beginning of the problem. We think, there's a lot of job ads here out there. The job posting in itself use a lot of biased words in it. So we want to change the word embedding in the job post in itself, so it will appeal to a larger range of people. So for example, if you look at, some people might say native speakers only when they look for a job, but what they mean is fluent in a particular language. And that way you're not excluding, say, immigrants. And some of the jobs might ask for, you need to have a driver's license or you need to be able to drive. What they actually mean is you need to be able to move from one place to another to conduct this job. But if you actually specify, what the content of that action is, that will kind of include people with disabilities. So from there on, we look at how application tracking systems actually work. So right now, it's mostly a negative filtering system. So negative filtering means we're looking for what you don't have in your resume. So we might say, oh, if this person doesn't have a bachelor degree or doesn't have a PhD, we don't want to recruit them. Instead of looking at the experience that you do have and how that might contribute to a particular job. So what we want to do is to change the negative filtering to affirmative filtering in the application tracking system. So then in this case, we will actually get candidates that are qualified instead of just meeting a set of arbitrary criteria. And then we look at the word embeddings in the application tracking system of how much importance they place on different words. So there's studies out there that talk about their feminine words versus their masculine words. And it's not in particular, like say the word collaborate, it's not a female only word, but it's used more often when we look at resumes of female than male. But then the resume scanners or application tracking systems actually learns this behavior and over time kind of places more values on words that are traditionally masculine. So we want to change the ingrained bias in this word embedding. But like even with all of these changes, there are still two main difficulties in solving the problems of building responsible AI applications and the bias. So one part is just bias built into the data set. And the second part is how do we define fairness? You know, how can we get to a place where we say, oh, this is fair, you know, this is fine, we're not doing any harm anymore. So the first part, so like when we look at bias built into the data set, say there's an online ad engine algorithm that's making assumptions that once you're a female in your 30s, you want kids. Then they will start showing you ads about baby clothings and nursery furnishings and all of these. Sorry. Oh, sorry, I'm just hearing my own voice. Okay, that's gone. So that's very hard and to change because historically that has been the case. But recently everything is changing, but all the algorithms are still trained on these old data set. So how can we change that over time? And then say you're building a speech recognition software and that's only trained on North American speech patterns. So it doesn't really function in any other geographic area. We probably all remember when, when Siri was just released by Apple a long time ago, it actually doesn't really recognize most people's speech patterns. And now it's improving because there's more and more data out there. So how do we mitigate like AI bias in this sense when you have some biased data sets? Like what can you do? So there are a couple of techniques that data scientists these days can use. Like most of them, the most effective ones are the pre-processing techniques when we're still at the data preparation stage. And then when we're at the model building stage, there are a couple ones. I'm not going to go into details on these. And then at the post-processing stage, when you're doing model valuations, you can also use some of this. So where you can go and find these is open source libraries like FairLearn by Microsoft and AI Fairness 360 by IBM. Watson, you can check all their documentations on this and see if this is something that you can incorporate in your work as well. So for us in the software that we built, we also build in some mitigation strategies. This is just a preview of kind of the type of platforms that we're currently building, which is auto-detecting all the sensitive attributes within the data set and outputting a customized list of fairness metrics that might be relevant for the cases that you're looking at and selecting the most relevant mitigation strategies for you. If you're interested to check it out, it's on demo.cosa.ai. So a particular study in bias is Google Pixel 6. They just released this phone a couple of months ago. And what they did for their camera tech is that this face detection model called Face SSD, they actually took the time to work with people of color and then trying to add different layers in their algorithm to mid and undertones. So the darker complexions will actually show better when it comes to compared to previous models. So this is one thing that you can do to actually, look at how we solve this particular bias issue when you don't have a lot of training data set and then there is a bias in your model that's built in. But what's difficult in this particular sense is sensitive attributes. When we're talking about sensitive attributes, it can be, race, age, gender, or your sexual orientation, your religion, anything that's protected under law. And then you can expand this to be, if you're building a healthcare algorithm, does this person have pre-existing conditions? Yes or no, that can be a sensitive attribute as well. Your zip code can be a sensitive attribute, but because that's highly correlated with your socioeconomic status. But what happens most of the time is there is no sensitive attributes within a data set. And that's the difficulty in deciding. If you don't have that information, you won't know, right? For a lot of financial institutes and healthcare companies, because they don't want to discriminate against people, when training a data set, the sensitive attributes are actually missing from the data set. So they're saying, oh yeah, we're not even looking at race, so we cannot be racist. But if you actually evaluate the outcome of the model, and then you attach race to the outcome, you can clearly see disparity. Then what do we do in this situation? Like it's really hard to decide whether we should include the sensitive attributes, because we need to measure it upfront, whether this is contributing to some disparity down the line, or we want to protect the customer's privacy, and then we don't want any demographic information in our data set. And this is probably one of the hardest problems to solve now when it comes to AI bias. How do we make sure this doesn't happen? Because the sensitive attributes are missing. There's a couple of ways to go around solving this, because there are a lot of proxy features that you can measure, like zip code. That's not really demographic information, but it's not the most ideal situation. But yeah, really want to hear what you guys think on this. But we can also solve this with another way to do this is to solve this with better data, a more wide range of data. If you look at natural language processing technologies out there, the most advanced are always for English speaking people. The English language just have so much resources to work with. If you look at support for Swahili, that's probably not there, because there's just not enough data out there for people to use. So to build better applications, we need better data. That's a slow progress, and there's a lot of kind of NGOs and foundations, including the UN, that's working on this. That's one of, I guess, the SDG goals a lot of companies are working towards. And then another problem we're talking about earlier is there are too many definitions of fairness, and many of them conflict with each other. I say about 20 definitions here, but actually there are over 70 if you really start looking into it. So if you consider these two definitions, one is demographic parity. So that means portion of a protected class, that might be gender, race, age, should receive positive outcome at equal rates. So that's demographic parity. And if you consider the healthcare algorithm, that just means everybody among different racial groups should receive equal amount of access to care. And then the second part is equalized odds. So the true positive rates and false positive rates are equal across groups. So that just means you're likely, like everybody within the same, between this different racial groups are equally likely to be rejected. So that's quite different, and depends on kind of your way of thinking about how you want to build an application. You have to choose a different standard to judge yourself. Say, I guess we can do a little poll here. Do you think college admission should be based on merit only? So only looking at your academic achievements and looking at your test scores and nothing else. I guess raise hands if you think this is a yes. We should only looking at merit. Okay. And how about, I guess, people that feel like, no, we shouldn't only looking at merit, that there's other things that we should consider when it comes to college admission. Okay. So I guess, it's about half and half. So if you say yes, that means we're looking at, regardless of the applicant's race, gender, like their socioeconomic status, if they're qualified, they will get in. If they're not qualified, they'll be rejected. So the metrics here we are using is to look at equalized odds. So if you say no, we shouldn't only looking at merit because there are structural bias in college applications and access to educational resources. So percentages of each group should be admitted similarly. And I think this is what we observe in the US, where there is affirmative action for people of color. And in this case, the metrics that we're looking at is demographic parity, right? So it depends on what you think is important. You should use different measures. And I think that's the hardest part. Like no one can really agree on this. If you look at a particular case when it's about criminal risk score, that a company is building algorithms to decide criminal risk score. And there was a huge profile about how this system is very, very racist. That was featured in ProPublica, and then it went on to be viral. But if you actually examine the case and how they structured it, to say it's very racist versus, oh, it's actually okay, they just used two sets of different metrics to measure the system. So this is I think, one of the hardest parts in solving this problem, to say, how can we agree on this is fair or this is not fair? I think this is more of a philosophical and political and maybe social questions to ask everyone. And the target will keep on changing. So we need to keep on updating kind of our own system to match up to this. So
Leila, sorry to interrupt, but can we start getting into the questions now? Because we only have about 13 minutes left.
Yeah, sure.
Is that fine? How many more slides do you have?
I think
maybe we can wrap up real quick.
Just one or two.
Okay, yeah, then we can wrap up.
So if you're interested in the reading materials here, there are two books that I highly recommend. One is Cassie O'Neill, her book on Weapons of Mass Destruction, and Ruha Benjamin, she wrote a book on Race After Technology. And there's a couple of TED Talks that you should check out, and the movie Code Bias on Netflix if you haven't seen this. If you want to learn more, you can also read our blog is City.AI at Medium. And one other thing, if you want to test out how you can incorporate responsible AI in practice, you can join our current beta. The website is Cosa.ai. Then you can test out how the application might be useful to you and in the process that we talked about before. So yeah, I guess we can get into questions.
Awesome.
Thank you so much, Leah.
Thank you very much. Yeah, maybe I can just read these questions here. There was one earlier, which I think has been answered now by Bibito in AI. What are allowed levels of bias? How do you make the evaluation? Yeah, Leila has quite a bit gone into that topic, I think. Bibita, did the rest of the talk answer your question, or you want to specify it a bit more?
Yeah, so I guess I'll go through some of this. Is like what level of bias are allowed? I think it's up to the maker, right? Like if you're a company that's making algorithm, you have to decide it for yourself. And then you need to be able to answer these questions when people ask you, and how do you justify that at an organizational level to say this is the amount of bias that's allowed. And then bias in itself, the word bias always implies some negativity, but it doesn't actually have to be bad, because like say I like apples but I don't like bananas, that's a form of bias. Is that bad? That's not really bad. But when we're talking about bias, it's more about unintended harms and discriminations, and you have to evaluate for yourself, like this is the type of company that we are, and then this is what we're presenting out there. And like someone, I think Kevin said, race is almost never an actual data point. Yes, that's what we're talking about when we're saying sensitive attributes, right? Like socioeconomic status, yes, that definitely is a sensitive attribute, but like how much of that do you want to allow into the computation of your algorithm? Like say you're a real estate company, you're using algorithm to make predictions on housing values, and that's very highly associated with zip code and which neighborhood you are, and zip code are associated with race. So you can say, oh yeah, this particular neighborhood, it's never gonna rise in value because X amount of factors. Or you can say, oh yeah, they're racist because there are a lot of Black people living here, and the real estate company never really estimated to be higher than wherever other races live. But is race the sole factor here? Probably not. There's other factors here. So that's like a complicated question that people, when you get into it, there are like different dimensions in which you can evaluate it and then decide for yourself like what level of this, I guess, sensitive attributes actually influence the model decision-making process.
Thank you. Yeah, then we have Mark asking, how will you regulate the training data being fed by a model that learning by itself or maybe learned by itself? So I guess this is different AI models feeding into each other.
I think it's always we're talking about uncovering bias in data, right? Like the same set of concept applies here as well. When you're looking at it, you first need to evaluate like the data that you use, whether it's fit for purpose or not. Then probably working with like domain experts to try and figure out if the data is how the data is collected, how the data is sourced, and apply, traditional statistics if you're looking at different set of metrics to evaluate the data. That can be done continuously as well. It's done on the data level. So like how the model uses the data is another matter. Yes.
All right, great. Then we have Kevin saying race is almost never an actual data point. The issue is that because of socioeconomic factors, some races are more disadvantaged than others.
Yeah, I think
we touched on that already in the talk quite a bit. Yes, then we have Ribo asking, how do you handle model performance when your data changes upstreams in the organization? So that's about the drift issue. Does that affect your bias on your model performance? Yeah, maybe you can talk a bit about the relationship between drift and bias.
Yeah, so I think drift and bias is not like particularly always linked, but what matters is when your model goes into production, you're actually continuous to monitor your model performance instead of, it's one and done, we built it and then it's in production and we're looking at maybe conversion rates or some of the more relevant commercial indicators of the model, but you have to monitor how the model in production actually impacting different groups of people. Like say, if you have a fraud detection model and it's working great, it's saving the company a lot of money and it's generating some revenues. But on the other hand, if you go deeper into the model monitoring, you might find out, for a particular group of people, the false positive rates are sky high. And that's when you should ask yourself, is this normal? Is this what we want to see? Because you're just negatively targeting a group of people based on one personal trait, most likely. Then that doesn't really impact model performance in any sense overall, but it does impact model fairness. And we should go back and evaluate the impact of bias in that sense. And you never really know, like that's when the sandbox environment is really important when you look at, if we adjust our model and if we resample part of the training data set to be more balanced and train it, it improves fairness in whatever metrics that you're using over time, but how is that impacting performance over time as well? Like sometimes we're seeing this like fairness going up and then the performance going down, but sometimes we're seeing like both of them going up at the same time. So this is very important to do a lot of exploratory analysis, and especially when it comes to bias, because that's almost never really a KPI set for any data science team or on an organizational level. Like people might say we have this list of principles, but it's not actually incorporated into the daily work. But we think it's very important that we do. So your technology are being inclusive, because they can quickly get to a point that, we don't have any human bias in our model because it's an algorithm handling this, and data are very subjective. But data are not subjective because historic patterns, human bias in the data, all those issues.
All right, thanks, great. There is, meanwhile, a second question. Okay, is there a way to do data traversal based on data used for governance and audit? I guess that refers to tracking where the data originates, maybe, or?
Yeah, so I think that's when we're talking about the whole pipeline of like our philosophy is not just looking at the algorithm, auditing the algorithm, right? Like documenting throughout the whole way, the reporting is quite crucial. As You guys probably have heard there is a Boston data set, an sklearn library that's open source, and a lot of people use it in training, and then probably a lot of schools also use that for student projects. They actually deprecated this data set. I think this year, like 2 or 3 months ago, because they discovered this Boston data set, which is a police data set. It is so biased that like whatever you use it for, it always ends up being, like Black people in the data set being punished. And so they deprecated it. And that's when, like if you document the data that you use and then you keep going back and looking at it and audit the data and then explore, how this data is being used, you will know stuff changes over time. And this doesn't fit with the current climate and the current kind of society standards anymore. Then like if you retire that data, any model that you use to train them to train the model on, you should probably also retire them as well or reevaluate them for drift and for bias.
Awesome, thanks. Yeah, I have a question of my own actually, which would be, so we have touched on basically different dimensions of the problem here, the different kinds of problems like bias, fairness, data drift. And then in fairness, we have multiple definitions, bias as well, etc. What happens if you add like intersectionality to that, like overlapping groups of that are victims of bias and fairness?
Mm-hmm. Yeah, so the intersectionality is super important. Like if you look at it from a purely technical perspective, if you're examining how the model impacts or the data imbalance, you're just taking this variable, whatever that variable that might be. It can be, gender, race, age, and these things. And then it's a statistical measure. So with the intersectionality, you can combine all of these different variables still into one and then say, oh yeah, this is not just, this person is not just Black, but also female, but also just disabled, and but also, of, I don't know, like in an LGBTQ community. And you can still combine all of those and then use the statistical, measures to evaluate for correlations and bias that way. But these cases are always more complicated than just like statistical measures, right? So that's when it comes to, we should refer to domain experts on how we actually work with this data, like what we need to look out for. So I think the study on the intersectionality of like these data, how we use these data and then bias within like technology is still very complicated. A lot of people are looking into it. It's probably going to keep on changing and it's a moving target.
Great, thanks. Yeah, very difficult problems indeed.
Yeah.
And thanks for touching on all that and going into the right level of depth here. I think awesome talk. That is very much giving a clear picture of this area, which is very important for particularly maybe for AI startups in the region also, because maybe in Africa here we have a different perspective and can actually push to get more recognition for these problems. It's not just some side problem of some people, it's actually what concerns most people here very directly. So thanks a lot.
I completely agree that if you see a lot of companies that's working on, building responsible AIs and then trying to solve the problem, there are a group of people all sitting in Silicon Valley trying to solve this problem, and then you would think, but what about different perspectives? What about Africa?
Yeah. Exactly. We have one more question. We have 1 more minute. So last question here is, can we use the quota notion used in statistics to control the data drifting and prevent the data bias by Ahmed?
Yeah, I think this is part of the monitoring process. Like for what we do is that you can use all of these statistical measures to look at, like the p-value, the chi-square test, like all of these things that you can set up. And then on top of the fairness metrics that you can set up as thresholds and then see how the data performs over time. And then if it crosses this threshold that you set for yourself, you get an alert, and then you can go back and look at this and then ask yourself the question, is this what we want to see? Is this the right amount of bias that should be present in our model? And are we treating people fairly? Should we go back and refit our model? So I think it's never really cut and dry to say this is when you should refit your model, or this is like really biased. It's just part of the monitoring process. Okay, I think that should be it. Thank you guys so much for having me. I'll talk to you later in the panel.
Thanks a lot, Leila. Yeah, thank you very much. That was awesome. Yes, so we are continuing on to the next talk. By the way, if you just joined or you joined during Leila's talk and you want to see it in full, then that was also streamed live on YouTube, where it will be for later viewing also. Just go to the City.AI channel. I can also post the link in a moment in the chat. Yes, and now we are continuing with a talk by Jaime de Miguel from AI Care, using car telemetry to predict driver safety. Yeah, very different topic, but just as interesting. So Jaime is the CTO and co-founder of AI Care Telematics in Kenya, previously PhD candidate in computer science and AI, as well as lecturer in data visualization and data science and big data master program of the University of Seville. He holds a background in architecture and design with master's degree from Architectural Association in London, and has developed a keen interest in computational modeling ever since. Jaime is responsible for leading the design of the sequential roof project of the ETH Zurich under Gramazio and Quota, and among other initiatives. Jaime is founder of Forma, an interdisciplinary workshop for complex systems modeling in humanities, introducing agent-based simulations to a large community of researchers in Andalusian universities. Yeah, welcome a fellow multi-agent systems researcher here. And yeah, Jaime, are you good to go? Can you share your screen, please?
Yeah, I think I'm good to go. So thank you very much for the introduction, and I'll share my screen, and once you can confirm it's up, I'll just start right away.
Yeah, please start.
So I guess it's up.
Yeah, we can see it.
Okay, perfect. Thank you very much. So my name is Jaime, as I have been kindly introduced. I'm a founder of iCare. We deal with telematics for the insurance and mobility sector. The business team have Arthur, which is having a lot of experience on risk. One of the problems we're trying to tackle here at iCare. We have a strong advisory team locally here in Kenya. I've myself co-founder with also a strong advisory team from University of Sevilla in the south of Spain. So the problem we're trying to tackle here with our startup, very young startup incubated originally by Antler last year in Kenya, here in Nairobi. And we found out that the insurance sector for motor had a lot of problems. So actually, one of the things that was really surprising is that most insurance companies here make a loss underwriting motor. Of course, these companies or most of these companies are profitable through other means, but the fact that their core business was not profitable was a very interesting call for us. So what we wanted to solve basically was reliant on the fact that insurance companies cannot assess risk very accurately because of many reasons, but basically they have very poor, in general, very poor KYC, know your customer. So no data on socioeconomic trends or socioeconomic facts about the people that they are underwriting, the people that they are insuring. or the vehicles that they are underwriting. One of the reasons for this is that the market is heavily intermediated. So intermediaries do not share a lot of information on the persons that are being underwritten with the policies. So that makes it really difficult for insurance companies to underwrite risk. So with telematics, we have a very good opportunity to tackle this problem by giving driver insights, in particular, driving behavior insights. So basically, our mission here is understanding how people drive, so that then insurance companies are able to assess that risk properly and price it accordingly. So basically, this is a little bit what our solution looks like. We want to be able to have, let me see if I can see my screen better. So basically what we want to have is like a score. Initially, we started out with a score for every policyholder in an insurance company's book. And for that, we have the collection of data through telemetry. Then we have an analytics engine, and then finally we arrive at the score. So breaking it down a little bit further, we have transmission of data in real time from the vehicles. We receive this data in our databases, and then we have an AI and machine learning engine that processes this data, and finally we share these insights for our insurance companies. A little bit getting closer now to the data that we collect. We collect this data right now with a telematics device that is wired into the car. It has a 2G GSM communication module. It has GPS, of course, 6-axis acceleration sensor, and a lot of some other features that are very interesting, like crash detection, towing, and some others. But generally, for the data that we're going to be studying here, the GPS and the accelerometer are the main sources of data. Then moving forward, we're also interested in looking at phones, mobile phones, as a means of collecting data. But right now, given the people's habit about usage of data, we think that the Kenyan sector is maybe a little bit too early for that. But that will be a very interesting move going forward. So the data we collect from the device is quite broad. Here's an example of the data that we have been using for the machine learning experiments that we have performed as of late. So the device will send to our servers, will send a message every 1 to 3 seconds when the car is moving. And each of these messages looks a little bit like this. There's more fields in the actual messages that the device transmits. But these are enough for the study that I'm presenting here. So for the study I'm presenting here, these are the fields that I have taken for each of the messages. Now, with that gives us kind of like an idea of the frequency of the data, as we said, like 1 to 3 seconds when the car is moving, and what are the kind of fields that we can get from there. So the problem we're trying to solve with the machine learning experiments that we're performing is that we want to be able to assess not just how well people drive with a kind of like a score, which is something that some companies in the sector have done, where you can, for example, count harsh events like harsh brakings, harsh accelerations, or over speeding, and then you kind of make a score where that accounts for penalizations for each of these incidents. So that's one option that is there already. That's actually how we're currently scoring our drivers with a little bit more sophistication, but that's not on the point here. But the idea of the real power of using machine learning in the way we understood it was to move from that kind of a score to actually be able to come up with an accident probability. Because if we're able to come up with an accident probability measure, then we could really know exactly what is the risk in terms of an economic cost, an economic liability. Say we know that, for example, a car has a 40% accident probability in 1 year, then that, given the value of the car, it's a lot easier to tie it up to an economic cost, an economic liability. So that's the challenge. That's the challenge that we're trying to do with these experiments here with machine learning. Now, the issue is that this is a very hard problem, because usually machine learning relies, especially like the statistical side of machine learning, not maybe the more formal and logics-based approach to machine learning. But is somebody talking? Sorry. So on the statistical side, machine learning, we need typically a lot of data samples. We need big training sets of data so that we can approximate functions, we can approximate patterns, we can identify patterns. So that is a big drawback, especially here, because if we want to predict accidents, we need a lot of accident data. And accident data, fortunately enough, is very hard to get. So even because thank God even there's a lot of accidents out there, that is a small number if we take into account the kind of data set sizes that we would need for such studies. Okay, so this means that we need to come up with some alternative approaches. We cannot just predict accidents by feeding a lot of accidents into a machine learning model and then coming up with regressions or correlations for each of those accidents. So one of the schemes that we thought could be interesting to follow was like, okay, we don't have a lot of accident data, but whenever we have an accident, we want to be able to understand how, for example, how other drivers, how the behavior of other drivers that have not had an accident is similar or not similar to the driver that just had an accident. Okay, so by doing that, whenever we have an accident, we can at least try to measure distance in some multidimensional space to the vehicle that had an accident and see if, you know, if there are proximities of behavior, and then the more accidents we get, we can go and start reinforcing those kind of clustering of drivers by behavior that are tagged or flagged to drivers that had an accident. Okay, so that's a little bit the idea, the approach that we want to take, that we think could be interesting to take. And then additionally, if we are able to do that, then by also understanding the speed profile of each driver and the proximity to a driver that has an accident, we could not understand just the probability of accident, but also the probability of accident at what speed, and the breakdown of those probabilities by speed, which would be very interesting because the speed is very obviously directly proportional to the severity of the accident and the economic loss of the accident. So what we have tried is we've done a kind of like a first attempt just to understand how we could, just to understand if we are able to cluster drivers together according to their behavior. So that if we are able to cluster them together according to their behavior, then we will be able, once one of them has an accident, we will be able to understand that the ones that are in the proximity of the driver that's had an accident could be at high risk as well, right? So our first approach is based on neural networks, and sorry. So our first approach is based on neural networks. Just a very quick introduction to neural networks. And they're based on how individual neuron works, where a neuron has a set of inputs, and then each input can be weighed by a certain weight. And then there's a single output, which is calculated as the sum of all the inputs multiplied by their weights. So it's very simple. It's a very simple principle. There's also an additional term here, which is the bias, which is not so important, but this is like the main principle of how it works. It's not exactly really how a biological neuron works, but it's a very powerful mathematical model. So if we cluster them together, then what we have is a neural network. So here, for example, if we focus on this neuron here, number 1, which is in a middle layer, which is called a hidden layer, then we can see that this one will work exactly as what we've seen in the previous slide. This neuron has 4 inputs, epsilon 1 to I, p, and plus 1, whatever. These 4 neurons are inputs for our neuron number 1. And the output that is going to this output layer is calculated exactly just how we've seen. So you can see that very quickly with this single neuron scheme, it's very easy to calculate all of the outputs for each of the neurons. Now, the trick of neural networks is basically that one hopes that by adjusting all the weights of all those connections, there will be a specific, one could find a specific configuration for all those weights that will be intelligent enough, for example, to differentiate between cats and dogs, or in this case, between cats, dogs, hamsters, and rabbits. So that is the hope for neural networks. And the process of adjusting all those weights is what we call training the network. So here, for example, what we would like to have is a total configuration of weights smart enough that would output here a value of 1 on this top output neuron. Then on the next neuron would output 0, then 0 again, 0 again, and if it were a dog, it would be 0, 1, 0, 0, etc. So the way that the neural network is trained to arrive at those results is by measuring error. So every time, for example, when we feed a dog through the input layer, every neuron here could be a pixel, for example, then we can measure, we can arrive at a result here for the output. Then we would have the expected output for a dog, which is 0, 1, 0, 0. And if we do the difference between these two vectors, that would be the error. And the error is fed back into the network to adjust all the weights. And that's how, in an iterative process that is repeated like thousands and thousands of times, we're able to adjust all these weights until whenever we feed this dog, it will output a vector that it's exactly 0, 1, 0, 0, or close to that with a minimal error. Now, one very interesting model for neural networks are autoencoders. Because in autoencoders, instead of doing classification, what we have is that we just try to replicate the same output. So we feed a cat and we expect to get out the same cat. Obviously, it will not be exactly the same. It will be a little bit washed. But that is something that allows us to train a neural network, minimizing error again, but not in the way we saw before, but just trying to reconstruct the initial input. But it will give us in the middle kind of like a condensed image of the pattern that is, the unifying pattern for all those types, in this case, cats. So that middle layer, called the latent space, will hold a kind of a representation of the unifying patterns that define cats, or at least the cats in the dataset. So the approach for us here is, can we imagine that this latent representation, this kind of condensed essence that represents the patterns, the unifying patterns for all those samples, if those samples are drivers or are driving trips, could that encoded representation become a sort of digital signature of our drivers? And if so, it would be very interesting because we could have, for example, a bidimensional space. That encoded representation could be of dimension 2 or 3, and then we could plot those points in a space that we can actually visually see and understand how close they are to each other. So with neural autoencoders, that is something that is very interesting as an approach, but it has a little problem. And the problem is that that latent space is very non-uniform. That means that, for example, if we trace all the dogs in that space, it will follow a very, very complex trajectory or distribution. So the distribution of dogs in that space could be very random. So in that space, we could have a dog and a cat close to each other, but they're actually very different because they're following complex distributions. So what we would like to know is what's the distribution that they are following, so that we could understand the distances between them. For that purpose, variational autoencoders, which came up around 2014 or 15, are a very interesting solution. So variational autoencoders, what they do is that they kind of build a distribution here in the middle. So we reserve 2 neurons for a mean value, a mean vector, and a variance vector. Because we want to build this Gaussian distribution, for example. It could be some other type of distribution, but we want to build a distribution that is easy and well known. And a Gaussian distribution, in this case, for example, it can be defined just by 2 values, a mean and a variance. So we try to build that thing in the latent space, or in in the central part of the autoencoder. And then what we do is that now the error that we're training for is kind of split into two. On the one hand, we want to train for the reconstruction error, but on the other hand, we also want to force that distribution to follow a Gaussian distribution. So then the output of the whole autoencoder, what we have on the latent space, will follow that distribution, or will be close to that distribution. So that's the target. So to measure the distribution difference between the Gaussian and the actual distribution, or any distribution for that sake, we use the callback labeler divergence metric, which just measures the difference between two given distributions. So now we are forcing this latent space to follow a more uniform distribution, while at the same time we're training the network to minimize reconstruction error. So that's very interesting, because now we could have the cats and dogs nicely tidied up in clusters that follow known distributions, where we can measure distances in a much better way. So what have been our results so far? Anticipate that they're not very good, but at least there are some I think some interesting insights. So for the training data set, we have not given the network just the raw data from the trips, but we have elaborated a vector of features. Okay, and we have also like set up a different options. So on the first option, we have 15 features, which are speeds, speed variations, angle variations, accelerations in X, Y, also acceleration from the accelerometer, acceleration from the GPS. So they're supposed to be similar, but and then we've also included how far, how much faster are you from a normal speed when you're approaching a stop or a corner. Okay, so that's a feature that we've extracted. So we've understood what was the normal speed at each meter, let's say, when you're approaching a corner or a stop, and then we've computed what's the difference from the actual speed that that car at which that car was driving. So, for example, if we're driving towards a corner at 20 meters, we should be at, the average value is, for example, 50 kilometers per hour. If you're driving 60, then that difference is going in here as a data point. So so these are 4 different options for input vectors. These are the inputs for the network. On the B option, we have a little bit less. On the C, we have even less. On D, we have a different combination. And for each of those, we have we've done batches of 150 messages. So that, at the 1 to 3 seconds per message, that's roughly like anywhere between 2 and 3 minutes. And then we've done larger batches of 300 messages, which be like around 5 minutes per batch. So you see the input size of the network would be, in one case, 2,250 neurons. On the other case would be 4,500 on the A option, and for the B, C, and D options, the figures are there. So that's kind of like to give a reference of the size of the neural networks, of the input layer of the neural network. So just very quickly going over the results. I know I have 2 minutes left. We should be fine. You can see that training over all the iterations has a clear overfitting. So what that means is, like here on the orange line, we see actually the real validation training. So this is basically really how the network is learning. And on the blue line, we have the training set learning. So this basically means that the model is, you know, computationally powerful, but there's not enough data to train the model. So after a little while, the validation curve just goes horizontal, and then this is a representation of the latent space. Each color is a different driver. Each color is a different driver, and you can see that there's no differentiation in the latent space. So on this other option, we have again a little bit less overfitting, but not a lot of learning. And now here on the latent space, we're starting to see a little bit of structure. Not a lot, but we're starting to see a little bit of structure. And then finally, this option with B, which had a little bit less input size, there would just 8 parameters in the input vector. Then here, we're able to see how finally there's been a cluster here and another larger cluster there, but still is not able to differentiate the cars, but it might be differentiating, for example, these trip segments of 3 to 5 minutes that, for example, might be where not much is happening, like straight lines, and here might be, for example, where you have curves or intersections, etc. Then finally, C and D, again, with only 5 input parameters on the vector, was not able to learn much either. So that's what we've done so far. I think there are interesting takeaways from this research. That would be great if you had comments or questions that we can discuss. Thank you so much.
Awesome. Thank you, Jaime, for this interesting detailed look into your methods and your results so far. That's great to learn about. We have one question so far in the chat. Ribo asks, how capture accidents from the car telemetry, or do you use alternative data to feed your model? So about how do you identify accidents?
So we can identify accidents because the device has an accelerometer, and with this accelerometer we are able to measure strong impacts. So if we have a strong impact, we can understand that there's been an accident. Actually, the range is also very differentiated. So when there is an impact, the range of acceleration goes anywhere between 10 to 20x. So it's easy to identify. But as I said before, fortunately, there's not a lot of accident data points happening. So you can't really rely on capturing accidents to train a statistical model. So it's better to come up with a different strategy.
All right, thanks. There's a new question by Manuel. Are there considerations on the terrain the vehicle is moving on?
No, right now, like there's possibilities to try to understand a little bit how the terrain is with the accelerations on the z-axis, which is very interesting. But at the moment, we are not including that on the accident probability model. That's something that we might try in the future.
Well, before I go to Next question. Sorry, you want to add something?
No. I was just reading the next one.
Okay. Before we go to the next one, I can maybe insert another one that I had, which is basically you say that you can determine the accidents from the data because of the amount of acceleration. And I guess acceleration is probably one of the most important features for determining driver safety, or at least that would be my intuition. You earlier said that you are sending data to the backend about once a second, and you gave us some example JSON data points which have acceleration. Is that acceleration like averaged over the 1 second, or how do you otherwise identify acceleration that is in below second time frame?
That's a very good question. That's a really good question. So what happens is when there is the device has an internal frequency of around 40 hertz for the accelerometer readings. So that means that's basically 40 acceleration readings per second. The thing is that it's not transmitting that data. It's only transmitting, as we said, every 1 to 3 seconds, right? So when there's an accident, then those 40 hertz are transmitted. And when there's not, there are what are called these harsh events. So whenever the device has an internal logic where it's averaging, like you said, over 500 milliseconds, it's averaging, and then when it goes over, that average goes over a certain threshold, then it sends a message. But that can only be used for certain, you can only get those harsh events. So to get to get like accelerations every second or every 1 to 3 seconds, then we have to use the GPS data. So that's one of the things where maybe using maybe on the mobile phone, collecting data through mobile phone or through devices that are not proprietary, like this one, where we have more freedom to adjust the parameters that trigger those acceleration messages, or more freedom to adjust how those acceleration messages are sent would be very useful.
Interesting. Thank you. We have a question by Bebeto. Can you give an elaboration on the score? Is it from 1 to 10, and what is the meaning?
So the score, so the scores that we're using right now is 1 to 100. That doesn't really matter. It could be 1 to 10 as well. And it captures a series of features going from these harsh events, accelerations, braking, cornering, to overspeeding and fatigue. And the meaning basically is trying to capture who is posing more risk on the road. So, if you're having a lot of harsh brakings or you're taking the curves at a very high speed, then we can understand that you have more risk of getting into an accident. That's just basically the meaning of the score. Now, the probability of the aim of the study is to assess not just a kind of like a rough score, but to understand what is your probability of getting into an accident, which would then not be a score, but an actual probability measure, a predictive probability measure, which will allow to tie up with actual accident cost in if that prediction was correct.
All right, yeah, thanks for that. We have another question by Nairobi, who's asking, how many cars and mileages do you have captured?
So right now we have about 60 vehicles on the road, and some of them have been on the platform for like two or 3 months, but some others have been in the platform for a whole year. So actually the study that has been that I've presented here captures anywhere between 9 to 12 months of data.
Okay, cool. Thanks. So I guess, I mean, maybe connecting to that from your experiments and the results that you've got so far, how much data do you think actually to need to get to, the model that you would be satisfied with for the business, A, and B, can that data be obtained only locally here, or do you need to add other cities and then try to find some maybe with similar driving behavior to make it work?
Yeah, I think like in terms of I think the effort should be on making the model more clever rather than acquiring more data. I think we do have quite a lot of data. From the experiments and this very early attempt, I would say that, you know, if I may go to the last slide, this one. So, for example, if what's happening is that most of the data we're feeding, this big cluster here, belongs to, you know, just like driving in a straight line, for example, that data might not be very relevant to the model because that is not a differentiating point between drivers. So if we want to differentiate between drivers, perhaps we should only feed the model those segments, those driving segments where something is happening. Because like even imagine yourself as a human, if you jump on all of these cars when they're driving in a straight line, would you be able to tell the difference on their driving behavior? So I think a lot of intelligence when building a model goes on choosing the right data set as input, the right input data set. So if we call all the trips or all the segments of trips, these 3 5-minute segments that we have been working with, and we call all of the ones that are kind of like irrelevant or boring because, you know, not much is happening there, and we just focus on those where there's more decisions from the driver, like how do I take the curve, how do I come out of the curve, how do I stop, how do I move forward. So that could start giving us different results altogether. So that would be like, let's say, future work. I think it would be focusing on selecting the data and the features that go into the model more intelligently. This was just like a first approach to understand how the model reacts to the data. So we've extracted a few features, but I think we can be a lot more conscientious about it.
Thanks. Yeah, very interesting indeed. Okay, John Bosco asks, what are the time intervals between data records and why the specific time record? Okay, I mean, we have already talked about that, I think, mostly.
Yeah, 1 to 3 seconds when the vehicle is moving.
Yeah. If you missed part of the talk, just a reminder, it's also live on YouTube. You can rewatch it there. Yeah, any other questions? Yeah, just putting the YouTube link in the chat as well. It will also be up there for later review. Right, last minute allotted to this talk is running. So if you've got a question, ask it now, or you can also contact Jaime afterwards, or on the, maybe Jaime can also hang out on the Gather Town. I don't know. We have the Gather Town for networking setup. So if you haven't done so, then at some point maybe try to go there. It's a nice little tool to have like a virtual conference setting where you can talk to each other. Yeah, inviting you all there. The link is in the boarding kit. You should all have the links also from your Eventbrite messages and page. All right, then it's 11:45, meaning time for our next item on the agenda for today, which is Utu's own Lea Njuguna, who is a senior machine learning engineer at Utu, where she explores innovative ways to use machine learning and artificial intelligence to improve the experience of a recommender system user. Oh, Jaime, have I actually thanked you? Thank you very much.
Thank you. Yeah, I was trying to say thank you as well. Thank you.
Sorry for that.
Thank you to the organization and to all the people in the audience. Thank you so much.
Yeah, thanks for that great talk. Interesting AI problem. Yeah, okay, back to Lea. So yeah, machine learning engineer at Utu. Her key focus is developing machine learning algorithms for the Utu trust engine that incorporates the social trust ensemble, as we call it. She also has the vast industry experience in the various artificial intelligence interdisciplinary fields such as natural language processing and computer vision. Lea is currently pursuing a PhD in statistics and has a Master's of Science in Actuarial Science from University of Southampton. She is passionate about equity in public education and supporting women in STEM. She is the member of the Women Who Code, as well as the Women in Data Science groups. In her spare time, she enjoys mentoring, traveling, curling up with a good book, and watching Friends on repeat. Welcome, Lea. And yeah, please share your screen and go ahead.
Thank you, Bastian, for the introduction. So let me share my screen. Is it clear to everyone?
Yeah.
So as Bastian introduced me, I'm the senior ML engineer at Utu. It's a local company. And basically most of the time I spend working on the recommendation system. And what we're trying to do is to come up with a social ensemble recommendation system where we put together the social relationships into the recommendation system. So before we go into my presentation of the day, this idea came up from Utu has basically a sister company called Maramoja, whereby it's a taxi, they have a taxi application. So the question was, is it easier if you are to get a recommendation for a taxi, is it easier you just go flag down a taxi and you get a ride, or would you be more comfortable calling someone that is related to you, maybe your brother, your sister, or your mother, and they recommend a taxi to you? And this is how the system Utu was born, whereby we look at the importance of social relationships in our lives. And now, because it is, you find that with the era of technology and AI, it will be easier to engrave the trust aspect into the AI systems. So Utu does that with the recommendation system. So basically, what is a recommendation system? WikiLeaks from Wikipedia, a recommendation system is an engine whereby we get the subclass of information filtering system that seek and predict the ratings of preferences for a user. But from my own understanding, the recommendation system is just basically a simple algorithm that gives you relevant information when you're coming to, or if you want to choose a product or a service. There are basically three types of recommendation system. One, we have the content-based filtering recommender systems, where we have, you have from the picture that is on the slides, you look at the user and the items that they've been using. If, for instance, it's like a movie they've been watching, and most of the time they like watching romantic movies or something like that. So there's a probability when you use the content-based filtering, you will find that you will be recommended definitely a romantic movie. This is an algorithm called the content-based filtering recommender system. The collaborative, and before I go ahead, for the content-based, mostly we use it in websites, social media, where you're given the list of things that you always prefer to maybe to read, or the pages that you always visit. For the collaborative filtering, which is very common in our day-to-day, the likes of Netflix, the likes of Spotify, is where we look at the similarity matrix, the similar users between user A and B. If user A likes this type of music or movies or books, and from the history of the user B, and because there's a similar tendency or preference of use of items, there's a probability that the list from user A will be given also to, will be recommended to user B. Finally, we have the hybrid approaches, because you find that the content-based and the collaborative filtering methods, they do not really have the accurate or the accurate recommendations that we really want in the AI era. So what do? We bring together the content-based and also the collaborative based filtering approaches, and we come up with better methods and to recommend. So what are we trying to do at Utu, and what are we doing at Utu at the moment? We have come up with a social ensemble, and ensemble basically in AI means that we have come up with one model and another and bringing them together. And at Utu, we have brought in the collaborative, we are using a collaborative filtering approach, but the selling point at Utu is that we are incorporating the social graphs, the social relationships. That is like, for example, myself, my brother, my sister. That network is put into the model, and it's analyzed, and now the user, my user preferences are also incorporated. So what this is, we are taking the implicit feedback. The implicit feedback contains all the user preferences for items and trust relationships between users. Implicit feedback means that anything that you have not been given by the user of your platform. For example, the number of clicks, the visits of maybe a certain social media page, that comes and couples the implicit feedback. The explicit feedback contains user item ratings matrix. A good example, you go to Utu, maybe you're a client, you go to a marketplace that is using the Utu ensemble, and you give us a rating of a certain, maybe you have bought a cup and you want to give a rating, so you give it 4 and you give the reasons of your 4. So that is explicit. This is the data that the client directly gives and you would want us to use. So during the social ensemble, there are different, there's the phase, the pipeline that we usually use. Normally, we start with the data collection, the data capturing, then where after the data capturing, we go to the data processing. The data processing, there two different data sets that we consider. The first one is the trust and the user reviews the trust. The trust means that myself and my brother, we trust each other. So there's always the trust statement that that goes into the trust data set. The second one is the user reviews data, where I had mentioned that you give a 5, maybe the star ratings or the reviews itself by giving a narration why you like the product or the service. In the same manner, we will collect the user ID of an active user to get a prediction of the recommendation from a specific model. In the data pre-processing pipeline, we will do the coding. There's the coding, there's the data formatting, that is the feature engineering, the treating of the nulls and the missing values. But also remember that because when we're using ratings data set, it is different. You can have rated book A, but also you have not rated book B. But that does not mean that the book B, the missing value of book B does not really mean it's a missing value. It's just that maybe you did not read that book. So you cannot remove that data set. So what we do when we are treating the nulls and the missing values, we only do it on the trust data set. But you just work with the ratings data set as it is. For feature engineering, you have to do it. Then during one important thing that I have to mention, we pass our data set through Neo4j. Neo4j is a graphing a platform whereby we look at the different types of influencers. If a node, we talk about nodes, if a node is influential or not. So we have to do an EDA, that is the exploratory analysis on the data. Then now there's the data distribution, where we'll pass the data through the model. For the model, we'll do two things. First of all, we have to create sparse matrices using either CSR or whatever method you're going to use in Python. Use Python. So we incorporate the social network information, which helps in predicting the preferences. And two, in case of missing ratings or we call it the sparse data, there's the infusing of the user item, matrix, and user social network for probabilistic matrix factorization. Why do you use PMF? We use PMF. The reason we use PMF is because if you look at on your left, from my side, it's on the left. Yeah, on the left, we have the social relationships. So you see that user 1 is connected to user 2, user 2 is connected to user 4, and user 2 is not connected to user 4. So this one, the data set is okay. But on your right, when you add the user ratings data set, you find that in the first user was rated Harry Potter. The first user did not rate the triplets of Belleville, but they were able to rate Shrek because maybe they had watched it. The second user did not rate or maybe did not watch Harry Potter. So you cannot say that the rating is 0. No, it is not 0. It's just that she did not, or maybe no recommendation was done. So this is where the importance of the probability factorization matrix comes in. It uses a Bayesian learning, whereby you're able to score or to do weighting using the same data, and you get a full matrix. And the sparse matrix is able to be filled up. And after it's filled up, this will be used. This will be used by the by our model. So as from our slide, you can see this is the social relationships, and from the social relationships you get the user ratings, and we combine that and we get a full data set which is going to be run through. After, definitely you have to do the training and the testing data set. So what are the advantages of using this? Using of the PMF and also using the network, the social network graph itself. First of all, through the UTU ensemble, we are able to use data that is sparse. That is, we do not really need a lot of data. Sparsity can come from the user. Maybe user A is still new to the marketplace. So what do? The model itself will identify user A is new in the marketplace. So it will able to get someone who is as equal to user A. Also, there's a product that can bring about sparse data. For example, if there's a new maybe drink in the market, and the marketplace, the social media wants to put it into the UTU marketplace. So what happens is the model will be able to identify that this product is almost or similar to this other product, and it will be placed in the right way. So for sparsity of the data set, we are not, it's already sorted out with the UTU ensemble. For this scalability, you can scale, the model is scalable, it can be used, right now we are in the small scale, but it can be used by other bigger, or it can go out. So for the integration of social network graph, we feel that this is very, very important, because you feel that with the era of the AI today, you find that you cannot really trust references from the internet, because some of these are bot, they are bot references, they are bot reviews, and some of these are like artificially made reviews, so you cannot really trust. But if you're given a reference and it's clearly explained that this reference, you have been given this reference because your brother or your sister or your mother had already used the same product or had visited the same restaurant, I think you'll be more at peace visiting such a place. So at the moment, we are on the first iteration of the model, and we are testing, we are having some issues, definitely challenges, especially when it comes to data sets. It's not easy to get data sets, and people are skeptical to release their data sets to us. So we have already done the first iteration of the model. So we are on the testing mode of our model with the Maramoja data set that we have in-house. So the next step is explainability. As there's someone who talked about having trustworthy autonomous systems. So this comes under explainability, comes under that you have to make sure that anyone who uses your system is able to get an explanation behind that. If I give you a recommendation of Cap A, why are you giving me a recommendation of Cap A? Yes. So that is where we are at. We are at our first and the second one. So mine was quite a short one, because it's not lengthy. So for us, for UTU, we are dealing with just bringing together the social aspect and bringing trust into our recommendation system. Thank you. So any questions?
Thanks, Leah. Okay, we have one question so far by Nairobi. How do you handle the cold start problem?
Thank you for that question. So for the cold start, if you look at the slide that I am at, so cold start is basically sparse data, meaning that a cold start means that we do not have so much data. So we invoke the probability factorization matrix into our model so that deals comes automatically and deals with this.
Thanks for that. Anybody else with questions? All right. Being from Uto myself, this is sort of a bit yeah, unfair, but I have still many questions about our own approach. So we have another question here from, again, Nairobi. How do you handle the computational cost associated with the user and item calculations?
Sorry?
How do you handle the computational cost associated with the user and item calculations? So I guess, okay, we are employing a couple of different algorithms here, as you have explained, and each of those has some computational complexity. Yeah, maybe you can explain a bit more about that.
Okay, I can take a go on that. So for the computational cost, at the moment, given that it's on small scale, we are trying for, when you invoke the probability factorization matrix, that means on Python, you're using the scarce matrices. You have to create the sparse matrix. So normally these user data sets, they have like, you have so many items, but the moment you create a sparse matrix on when you're modeling, it means that it compresses that data set. It gives you the zeros, a matrix that has majorly zeros, meaning that there's no one time that the computational cost will go high. So the difference between our approach and others is that you use the probability factorization matrix that deals with the computational costs.
Okay, does that answer your question, Nairobi? That's okay. Okay, I guess that means okay. Okay, thanks. Yeah, my own question that I was getting at was, so you mentioned, okay, so far we have only applied this model to one real world use case of ours, Malamoja, and we have also applied it to a few publicly available data sets, played around with that. From that experimentation and also from theory, so given that we are using a Bayesian learner here, how well do you think the model be applicable across different use cases, or do you need to completely retrain everything for each new sector? Like, okay, we have taxis. What's the similarity of trust behavior and rating behavior? I mean, okay, the model really here.
Sebastian, I lost you, sorry.
Oh, so, yeah, repeat. So you have a learner here basically establishing a sort of relationship between social connections between users and their rating behavior. And is that at all transferable between use cases, like different ones, like movies and taxi drivers? Or is it completely different?
No, that's that is where the EDA, the data, especially the data processing, comes in. So when you're labeling, the labeling, all that will be done in the labeling phase, so that there's no one time that you have to be changing each and every time you have to be changing or customizing the model. No, so that falls under the data preprocessing. So it will cut across all the industries.
Okay, interesting. Thanks. Do you have any more questions?
Any other questions?
All right. Thank you all then. You find Leah and also the ambassador team, and yeah, which coincides basically with the Utu team right now, on the Gather Town, where the networking is taking place. There's also the Discord. You can find all these links in the presentation, the boarding kit presentation that you should all have gotten, and also on the Eventbrite pages. So if you have more questions for Leah, you can still ask them now because we have a few more minutes, or you can find her on the Gather Town. Yes, thank you, Leah, otherwise, for that talk. Very interesting. Okay, natural for me to say because it's my own company, which is concerned, but yeah, if it wasn't interesting, then maybe we wouldn't be here. Well, so okay, let me just paste the Gather Town link in the chat. And Discord. So yeah, as I mentioned earlier, but for the newcomers, we currently are a bunch of people here: Leah, Rahul, Zakia, myself, and Shiku has left, I think. Okay. Anyway, so that's the current City.AI Nairobi ambassador team. We are all at Utu Technologies right now. If you are interested in joining City.AI as another ambassador in Nairobi, we are welcome to extend the team or evolve it over time. Yeah, to make it maybe less Utu biased, so to speak. City.AI is a community of global, yeah, cities with AI applying organizations, mostly companies, but also others in those cities. And yeah, basically each of those cities is running AI related events from time to time. This current festival is being run after a pause due to COVID. Yeah, to get the community back together. Yeah, if you join that Discord, you can also talk to other people there from other City.AI cities, and yeah, get connected more globally. Yeah, thanks all for attending to these talks. We have now a break for networking and lunch. Yeah, as I said, please join the Gather Town and the Discord. And on the Gather Town, there will also later be, after the talks of the day, the talent show with people displaying their personal projects and or research. Yeah, if anybody has any more comments, please go ahead. Otherwise, see you in the Gather Town. But you're also, of course, welcome to just stay on here and chat here. It's a very free form organization in that sense.
Thanks, Bastian. Yeah, I'll be in Gather Town if anybody wants to chat.
All right. Thank you all, then see you in Gather Town and later again here. Next up here will be the panel at 2 o'clock. Panel about skills requirements for AI workers?